Okay, so today we are going to learn the basics of IC design and relate any concepts related to that. So I'm going to document this. Okay, so this is MMIC development. So that's what we are going to do. And for this purpose, I'm going to use ADS for most of our development. Okay, so that being said, let's start with ADS. What I'm going to do is to explain. I'm going to use a scratch pad over here. Okay, so I have just launched ADS. ADS is a circuit simulator. It can do layout, it can do EM simulation, it can do system simulation, it can do behavioral level simulation on RF, it can do behavioral level simulation for baseband, for any modern communication system, right? So the concepts are very simple. Um, any circuit has has got active devices. So if I refer to any integrated circuit, so I have got active devices. Okay. So what I mean by active devices, these devices can receive energy in one form and convert into another form. So the simplest is they can take a power in as a DC from a DC supply source and can convert into RF. Okay, so these are active devices. They can also transform power, right? They can transform power from a low power to high power, so that will be called amplification, right? So active devices basically deal with powers, right? So they deal with either converting one form of energy into another, or basically increasing the power level or decreasing the power level, things like that. Right? So those are active devices. An example of these active devices are going to be transistors. So transistors, there are two concepts. One is called bipolar junction transistor, which is basically two diodes which are connected back to back. So that is called a BJT, and we will go into detail of BJT and then specific kind of BJT called HBT, right? So in development we will do that. Next is we have a device which is based on operation of fields on carrier. So there are two fields. One is the horizontal field, other is the vertical field, and the carriers are moving under the influence of two fields. So these are called field effect transistors, right? Then there are various variations of field effect transistors, right? So the simplest of them is a metal oxide field effect, semiconductor field effect transistor, MOSFET, right? So now, as the name suggests, it's a metal and then an oxide and then a semiconductor, and this sandwich structure is used for controlling the carriers between source and drain, two of the terminals, right? So these days we don't use metal, so basically this name is not exactly correct. We take the gate oxide, and top layer of a gate oxide we implant with ions, and then it becomes a conductive poly. So the gate, which basically controls the flow of carriers between source and drain using a vertical field. Okay, so that basically is no longer using a metal, it is using a conductive polysilicon. So field effect transistor, so simplest is a MOSFET. Then we have a metal junction, right? So it can also be used as just a metal junction with semiconductor, so that will be called a MESFET. Right? And then there are other variations of it, like for example, they call high electron mobility transistor or HAMT. right? So this is a specific type of field effect transistor. So let's put here. So we have MOSFETs. Okay, most of the silicon is dealing with MOSFETs. Then we have got what you call MOSFETs. Okay, MOSFETs, or junction field effect transistors, right? You can call it that way also. Then there are something called HAMs, high electron mobility transistors. This is something to do with very thin channels, and when the channels are very thin, right, then the carriers are almost confined to a 2D structure, and when they are confined to 2D structure, they don't have a lot of carrier interaction. That's why they have a high electron mobility. So that's why this device is called high electron mobility transistor. And then there is something called PHEMT, which is pseudomorphic high electron mobility transistors. So these various transistors are available. This is mostly CMOS, and then the remaining can be gallium arsenide, or it can be gallium nitride. So as we go in developing, we will scale various transistors. BJT has one variation. It's called HBT, and then this HBT again has got two variations: single heterojunction bipolar transistor and a double heterojunction bipolar transistor. Okay, so these are active devices. So they involve some form of a material which is a semiconductor. So we'll come to know what is a semiconductor later on. Okay, so when I detailed it. Now the next thing which we need is how to connect these devices together, right? So we need something called interconnect. So interconnects are nothing but these are thin traces of metal. Earlier there used to be a lot of use of aluminum, and then they moved to a lot of use of copper, and then they have no just because of the surface finish, they started using gold. But high frequencies, you see a lot of interconnects are gold. That is because of the surface finish. Just that the conductivity is not so good, right? So for example, here we are in the range of 3 into 10 raised to 7, okay, Siemens per meter. Copper is around 5 point something, right? 5.8 something. These are rough numbers. You can find exact numbers. Gold is around 4.1 into 10 raised to 7 Siemens per meter. And then silver. Okay, silver is also used in some cases. It is 6.2 into 10 raised to 7 Siemens per meter. Now, if you look at this, you would prefer silver, right? Because its conductivity is more. But you still prefer gold when it comes to microwave. It's just because the surface roughness is very important at microwave frequencies. We know that if we consider a cross section of a conductor, right? So let's say this is a conductor, okay, a wire. Then most of the surface would be where the currents would reside. So the currents would reside in the surface and up to the skin depth. So the center of the conductor will not have any current flowing at microwave frequencies. So if the conduction of current is on the surface has to be a fine finish. And that's what the gold does, right? Otherwise, we could have preferred silver because it's highest conductivity, or we could have preferred copper. And we do prefer copper in many semiconductor processes. Earlier, there used to be aluminum, but aluminum has an issue that it corrodes easier than copper, and gold is basically inert, or silver is inert. So oxidation of exposed metal is not a problem. Now, so there are two parts to integrated circuit design, and you have to understand, right? You have to understand that you should know devices and you should know interconnects. Now, there are some specialized shapes. Okay, so using some specialized shapes, I can make passive devices. So let's say, what are the various passives? So these passives can be basically power dividers and combiners. Power dividers slash combiners. Basically, these are bidirectional devices. So basically, you can change the direction. So outputs can serve as inputs and inputs can serve as outputs. So these are power dividers and combiners. Then you can have what you call hybrids. Okay. And these hybrids can be 90-degree hybrids or 180-degree hybrids. They are also 180-degree hybrids are also known as rat race, right? So we will see hybrids. Besides that, there is another circuit which is called balanced unbalanced, BALUN. Balanced unbalanced, these are transformers, right? So all these are required in designing microwave circuits. Okay, and these microwave circuits they are referred to as MMIC, monolithic microwave integrated circuits. Now if we were to take just the devices and then assemble them on PCB, right? Then they will be called microwave integrated circuits. They are not monolithic, right? Monolithic means that they are on a single wafer, while MIC means that they are using some kind of a carrier or a laminate or a board, right? Or a PCB, right? So that's what it is. So this is a brief introduction to ICs. ICs are nothing but they are circuits, electrical circuits, which have a specific function, and they can be designed using active devices, or they can be and then they can also be designed using just the passive devices or a combination of both active and passive devices. So we will see lots of examples on these, right? So this is for the first session, right? So I am going to stop here for the questions.